Welcome to the Deep Dive. Today we're diving into the world of competitive coding,
So cool.
specifically a problem from AI CodeCast.
Okay.
It's a daily challenge platform that I actually contribute to.
Wow. Nice.
And this particular problem is all about tournaments and champions.
Right.
So imagine this.
Okay.
You're given a tournament structure where teams play multiple matches.
Okay.
It's not like a simple knockout.
Right.
Your task is to find the champion,
Okay.
the team that's undefeated.
That sounds intriguing. So it's like a more complex version of a regular tournament bracket
Yeah, exactly.
where, we need to figure out who reigns supreme
Right.
among a web of wins and losses.
Exactly. The challenge lies not just in identifying the champion,
All right.
but also in efficiently handling cases where there might not be a single undefeated team or where there are circular victories.
I see. So those classic edge cases where it's not always a clear-cut winner
Yeah.
adds a whole new dimension to the problems. Before we jump into the solution,
Okay.
could you elaborate a bit more on the problem's input format?
Sure.
How is the tournament information presented to us?
Great question. We're given the number of teams participating, let's say N,
Okay.
and a list of match results.
Okay.
Each match result is presented as a pair,
Okay.
indicating the winner and loser of that specific match.
Right.
For example, Team A, Team B would mean Team A defeated Team B.
So we essentially have a list of duels.
Yeah.
And we need to analyze these individual battles to crown the overall champion.
Mm-hmm.
Feels like a puzzle where we need to connect the dots between these matches
Yeah.
to find the ultimate victor.
Right.
Where do we even begin to unravel this?
Well, one approach that might instinctively come to mind is the brute force method.
Okay.
We could go through each team and check if they've lost any matches.
Okay.
If a team has a single loss, they're out of the running.
That's a reasonable starting point,
Yeah.
like manually inspecting each team's record. Right.
And eliminating those with blemishes on their scorecard.
You're right.
But I imagine this method might become quite cumbersome
Yeah.
as the number of teams and matches increases.
You're absolutely right.
Yeah.
The brute force approach, while simple to understand, doesn't scale well.
Right.
Imagine a tournament with hundreds or even thousands of teams.
Yeah.
Checking each team individually would become incredibly inefficient.
So we need a more sophisticated approach.
Yes.
Something that can handle the complexity of larger tournaments.
Yeah.
Without, bogging down our code.
Right.
What are some potential pitfalls or tricky scenarios we need to watch out for?
One major pitfall is the possibility of cycles.
Okay.
Imagine Team A beats Team B.
Mm.
Team B beats Team C.
Okay.
And then, to everyone's surprise, Team C beats Team A.
Wow.
In this scenario, there isn't a clear champion as everyone has lost at least one match.
That circular victory scenario. A true conundrum.
It is.
Highlights the need for an algorithm that can detect these cycles.
Yeah, and handle them appropriately.
Right.
Another edge case to consider is the possibility of multiple undefeated teams.
Oh, good point.
What if two or more teams manage to go through all the matches without a single loss?
That's a great point. We need to ensure our solution can correctly identify such scenarios
Right.
and indicate that there isn't a single champion, but rather a tie at the top.
So how do we move beyond the brute force method and design a more efficient and robust solution?
Here's where the power of graphs comes into play.
Okay.
Instead of thinking about teams and matches in isolation, we can represent the tournament as a network.
Okay.
Each team becomes a node in this network,
Right.
and an arrow, or directed edge, connects the winner of a match to the loser.
So we're essentially visualizing the tournament as a flow chart
Yeah.
where the arrows indicate the direction of victory,
Yep.
leading us from the winner to the vanquished.
Right.
This is a great way to see the big picture and understand the relationships between the teams.
Exactly. And this network structure has a specific name, a Directed Acyclic Graph, or DAG.
Oh, okay.
The acyclic part is crucial because it means there are no cycles in the graph,
Right.
which directly addresses one of our pitfalls.
That's a brilliant insight. By representing the tournament as a DAG,
Yeah.
we eliminate the possibility of those circular victory scenarios that would trip up our brute force approach.
Right.
But how do we actually use this DAG to pinpoint the champion?
Well, think about the defining characteristic of a champion.
Okay.
They're undefeated.
Right.
In our DAG, this means there should be no arrows pointing towards the champion node.
Okay.
In other words, there are no incoming edges to the champion.
I see. So the champion stands alone at the top.
Yeah.
Untouched by any arrows of defeat.
Yeah.
Makes perfect sense visually.
Yes.
But how do we translate this visual intuition into a concrete algorithm?
Here's where the concept of in degree comes into play.
Okay.
In degree simply refers to the number of edges pointing towards a particular node. Our champion, being undefeated, will have an in degree of 0.
So if we can calculate the in degree for each team in our DAG,
Yes.
the champion will be the one standing out with a big fat 0.
Right.
A perfect score of no losses.
That seems like a much more efficient way to identify the champion than the brute force method.
Absolutely. And there are some very clever ways to calculate these in degrees, which we can delve into further.
I'm eager to explore those methods.
Okay.
But before we do, do you think it would be helpful to illustrate the DAG concept with a simple example?
Yeah, sure.
Just to ensure everyone's on the same page visually.
That's an excellent idea.
Okay.
Let's say we have a mini tournament with just 4 teams.
Okay.
Team A, Team B, Team C, and Team D.
Okay.
And let's say the match results are Team A beats Team B,
Okay.
Team B beats Team C,
Okay.
and Team D beats Team A.
Okay. I can picture that.
All right?
So how would we represent this tournament as a DAG?
We'd start by drawing 4 nodes,
Okay.
1 for each team. Then, based on the match results,
Okay.
we draw an arrow from Team A to Team B,
Okay.
another arrow from Team B to Team C,
Okay.
and finally, an arrow from Team D to Team A.
I see it now. The arrows clearly show the flow of victory,
Yeah.
and there are no cycles. It's a true DAG.
Exactly.
Now, looking at this DAG,
Mm-hmm.
can you point out the champion?
Let's see. Team D has no arrows pointing towards it,
Right.
meaning its in degree is 0.
Okay.
So in this mini tournament, Team D is the champion.
That's a fantastic illustration.
Yeah.
It really brings the DAG concept to life
Right.
and shows how we can visually identify the champion based on the absence of incoming edges.
Exactly. And this visual intuition is what will translate into a robust algorithm
Okay.
that can handle tournaments of any size and complexity.
This is where it gets really interesting.
Sure.
What are some approaches to calculate those all-important in degrees
Mm-hmm.
and efficiently crown our champion?
Well, there are a couple of clever methods we can explore. One involves using a Boolean array,
Okay.
and another leverages an array to directly store the in degrees.
Right.
Both approaches have their own nuances and efficiencies,
Okay.
and it's worth diving into each of them.
Let's do it. I'm ready to unpack these methods and see how they stack up against each other
All right.
in the quest for finding the champion.
Sounds good. Let's start with the Boolean array approach. It's a simple yet effective way to keep track of which teams are still in the running for the championship. We initialize an array where each element represents a team, and initially every element is set to false. Think of it as giving every team a clean slate at the start of the tournament.
So it's like a checklist
Yeah.
where everyone starts off as a potential champion.
Right.
And as the tournament progresses, we mark off those who have suffered a defeat.
Precisely. We iterate through the list of match results, and for each match, we mark the loser as true in our Boolean array. This indicates that they've lost a match and are no longer a contender for the champion title.
It's like a process of elimination where each loss gets you crossed off the list. At the end, we just need to scan this Boolean array and see who's left standing with a false value. That lucky team will be our undefeated champion.
Exactly. However, there's a slight twist.
Okay.
We need to ensure that there's only one false value remaining. If we encounter multiple false values, it indicates a tie at the top, meaning there are multiple undefeated teams.
Ah, that makes sense. So it's not just about finding a false, but also ensuring it's the only one. A true champion stands alone at the top.
Absolutely. This Boolean array approach is quite straightforward and efficient for tournaments with a clear hierarchy of wins and losses. However, it has a limitation when it comes to those tricky circular victory scenarios we discussed earlier.
Right, because in a cycle, every team involved ends up with a loss, even though there isn't a clear winner. So they'd all be marked as true in our Boolean array, wouldn't they?
That's exactly the issue. The Boolean array approach doesn't have a mechanism to detect or handle these cycles. It assumes a linear progression where if Team A beats Team B, then Team B can never beat Team A.
So for those more intricate scenarios, we need a method that goes beyond simple win-loss tracking, something that can analyze the network of relationships more deeply.
You're spot on. And that's where the in-degree approach steps into the spotlight. Remember, in degree is all about counting the number of incoming edges, the arrows pointing towards a particular node in our DAG.
Right, the higher the in degree, the more losses a team has accumulated. And our champion, with a perfect record, will have an in degree of 0.
Precisely. To implement this approach, we create an array to store the in degree for each team. Initially, we set all in degrees to 0, giving every team a fresh start.
So we're starting with a clean slate,
Yeah,
assuming everyone is undefeated until proven otherwise.
exactly. Then we go through our list of match results, our edges in the DAG. For each match, we increment the in degree count of the losing team. If Team A beats Team B, we add 1 to Team B's in degree count.
It's like tallying up the losses for each team,
Hmm.
keeping a score of how many times they've been defeated.
Indeed. Once we've processed all the match results, we simply scan our in degree array. Any team with an in degree of 0 is a potential champion.
Okay, so it's like looking for those who haven't been touched by any arrows of defeat. They're the ones who've managed to navigate the tournament unscathed.
Exactly. But remember those edge cases? We need to handle scenarios with multiple undefeated teams or those pesky circular victories.
Right. How does the in-degree approach address these potential pitfalls?
That's where the beauty of this approach lies. If we find multiple teams with a 0 in degree, it clearly indicates a tie. There's no single champion, and we can appropriately flag this scenario.
So it's like a built-in tiebreaker. If more than one team remains undefeated, we know there's no clear winner.
Precisely. And for those circular victories, the in-degree approach handles them elegantly. In a cycle, every team involved has at least one incoming edge, meaning their in-degrees will never be 0.
Because they each lose at least one match within that cycle, right?
Exactly. So when we scan our in-degree array, these teams won't even be considered as potential champions. The cycle is automatically filtered out without any explicit checks.
Well, that's pretty neat. The in-degree approach elegantly sidesteps those tricky scenarios that tripped up the Boolean array method.
Indeed. By focusing on in-degrees, we get a clearer picture of the tournament's hierarchy. It allows us to handle complex scenarios and efficiently pinpoint the true champion, or lack thereof.
Both approaches have their own merits. The Boolean array is simple and intuitive, while the in-degree method provides a more robust solution for handling complex tournaments.
You've got it. Now let's shift gears a bit and delve deeper into the efficiency of these approaches. How do they perform when faced with larger tournaments, say with thousands of teams and matches?
That's a crucial question. Scalability is always a key consideration in algorithm design. We want solutions that can handle real-world scenarios, not just toy examples.
Absolutely. And both the Boolean array and in-degree approaches perform admirably in terms of scalability. They both have a time complexity of OM plus M, where N is the number of teams and M is the number of matches.
So even if the tournament size grows significantly, the time taken to find the champion increases linearly. That's quite impressive. It means our solutions can handle even the most massive tournaments without breaking a sweat.
Precisely. However, there's a subtle distinction in their practical performance. The in-degree approach might have a slight edge because it directly calculates and stores the number of losses. This eliminates the need for additional scanning, like in the Boolean array approach.
So it's like having a pre-calculated scorecard
Yeah,
versus manually checking each team's record. The in-degree method streamlines the process and potentially saves some computational steps.
you've got the idea. But it's important to note that both approaches are perfectly viable. Choosing between them might depend on factors like code readability or personal preference.
Right. It's like choosing between two champion athletes, both capable of winning the race. The decision might come down to subtle differences in style or the specific demands of the competition.
Exactly. And this brings us to a crucial point. Understanding the trade-offs involved in different algorithms is just as important as writing the code itself.
It's not just about finding a solution that works, but finding a solution that works well and fits the specific context of the problem.
Precisely. It's about balancing efficiency, readability, maintainability, and scalability to create code that's not only functional, but also elegant and robust.
That's a great takeaway. It's about being a coding strategist, not just a code monkey.
Absolutely. It's that strategic thinking, that ability to analyze, optimize, and adapt that truly elevates a programmer's skill set. And the best way to develop that mindset is through practice and exploration. Don't be afraid to experiment with different approaches, analyze their strengths and weaknesses, and constantly seek ways to improve your code.
All right? It's like in any sport, you don't become a champion by just showing up. You need to train, analyze your performance, and constantly push yourself to be better.
Precisely. And just like an athlete studies their opponents, a programmer should study different algorithms and data structures, understand their nuances, and know when to use each one effectively.
So it's a continuous learning process,
Yes,
always striving to expand our coding arsenal and refine our strategic thinking.
exactly. And with that in mind, let's wrap up our deep dive into finding the champion. We've explored the problem, dissected different approaches, and discussed their trade-offs. Hopefully, this has given you a glimpse into the fascinating world of competitive coding and the power of algorithms.
It's been an enlightening journey, and I'm sure our listeners are now equipped to tackle similar coding challenges with confidence.
I hope so. Remember, the real champion is the one who never stops learning and striving for excellence.
It's amazing how a seemingly simple tournament problem can unveil such intricate algorithmic solutions. It really highlights the power of computational thinking and how we can leverage it to solve real-world challenges.
Absolutely. And what's particularly fascinating is how this problem connects to broader concepts in graph theory and computer science. For instance, the idea of in-degree is closely related to concepts like network centrality and ranking algorithms.
You're right. It's like we've stumbled upon a fundamental building block that has applications far beyond just identifying the champion of a tournament.
Exactly. Think about social networks, for example. We could use similar in-degree analysis to identify influencers or key individuals within a network, or consider web pages and hyperlinks. The in-degree of a web page, the number of links pointing to it, is a crucial factor in search engine rankings.
That's a great point. It's like we've uncovered a hidden gem that has the potential to unlock insights in various domains.
Indeed, and this is just one example. The world of algorithms is vast and interconnected, and often the solutions we develop for one problem can inspire solutions in seemingly unrelated fields.
It's like having a versatile tool in our coding toolbox that we can adapt and apply to diverse challenges.
Precisely. And that's the beauty of computer science. It's not just about writing code, but about understanding the underlying principles and applying them creatively to solve problems.
Okay, I'm feeling inspired to go explore more of these algorithmic connections. But before we wrap up our deep dive, is there any final piece of advice you'd like to share with our listeners, especially those who are just starting their journey into the world of competitive coding?
One crucial piece of advice I'd offer is this: don't be afraid to start simple. When faced with a challenging problem, break it down into smaller, more manageable steps. Often, the most elegant solutions emerge from a clear understanding of the fundamental logic.
That's great advice. It's like building a complex structure brick by brick, starting with a solid foundation.
Exactly. And don't underestimate the power of visualization. Drawing diagrams, sketching out graphs, or simply visualizing the problem in your mind can often lead to breakthroughs.
Right. It's like having a mental whiteboard where we can play around with ideas and see the problem from different angles.
And lastly, embrace the learning process. Competitive coding is not about getting everything right on the first try. It's about experimenting, making mistakes, and learning from those experiences.
It's like any skill mastery comes from practice, perseverance, and a willingness to embrace challenges.
You've got it. So to all our aspiring coding champions out there, keep exploring, keep learning, and most importantly, keep having fun with the process.
Wonderful advice. And on that note, we've reached the end of our deep dive into finding the champion. I hope you've enjoyed this journey into the world of algorithms and problem solving.
It's been a pleasure sharing these insights with you and our listeners. Remember, the journey of coding is an ongoing adventure. There's always something new to